Okay. Okay, so first and foremost, guys, chapter 8 is going to be combined with chapter 9. Okay, chapters 8 and 9 are all about bonding. This is the section where the big topics are going to be what are actually my favorite of the whole year. Not that that matters to you at all, but chapters 8 and 9, when we get to the end of that, and we're getting ready for the test, the big topics are drawing Lewis structures and predicting molecular shape. Do you guys remember from Chem 1, like tetrahedral, trigonal planar? Do you remember that? I mean, sort of. Okay. That's what we're leading into. Now, obviously, there's other topics here, and we're not getting into any of that today. Okay, but that's kind of where we're going. That's where we're headed. Okay, so chapter 8 is all about bonding. Okay, and before we get into any of the specifics, I just want to make sure that you guys are completely aware that a chemical bond is not something you can touch. Okay, it's not like a string that's tied together, tying two atoms together. It's not something you can physically touch. You know, when you're a little kid and you play with magnets, you can feel a force of either attraction or repulsion when you put two magnets together. It's like that. Okay, a chemical bond is a force holding two particles together. You can't touch it. It's just a force. Okay? And we're going to talk in this chapter about bond energy, okay, which is defined as the energy required to break a bond, okay? And I want you to focus on this word right here, required. If we say that energy is required for something, does that sound endo or exo to you? Endo. Okay? And it is. Bond energies, let's see what you remember. Are endothermic energies positive or negative? Positive. Bond energies are always going to be positive because they are endothermic energies. Okay? Heat is required. How large that bond energy is will give us information about how strong that bond is. Okay? So for example, guys, if we are dealing with a very, very strong bond, is it going to have a large number or a small number for the bond energy? Large, yeah. A large amount of energy is required to finally break it apart. Okay? So the stronger the bond, the higher the bond energy. Okay, so we can talk about energy, we can talk about bond length, okay? What is the distance between two bonded particles? And it says here that the distance is going to be determined when the energy of the system is at a minimum. This is better illustrated with a graph, ladies and gentlemen. And we're going to read this graph sort of backwards. We're going to read it from right to left. Okay? And what we're bonding together, these are hydrogen atoms. Now you guys tell me, how does hydrogen exist in nature? H or H2, what? H2. It's a diatomic element. You can think of that as like hydrogen prefers to be bonded to itself than alone. Okay? Well, we've got two hydrogen atoms, and we're going to read this graph from left to right, or right to left. Okay? You've got to bring them close together. Okay? If you have two hydrogen atoms that normally would bond, if you have them too far apart, they're not going to bond. You've got to bring them kind of near each other, and so that's what we're doing. We bring them near each other, and and we push them a little closer together, and we push them a little closer together, and a little bit more closer together. And then I keep pushing them together. All right? So here's what's going on. There's like a happy medium. There's a happy distance, okay, where these two particles will bond. Okay? If they're too far apart, they're not going to bond. If they're too close together, you start getting forces of repulsion. Now this graph right here says nucleus, nucleus, repulsion. Why would the two nuclei of these two atoms repel each other? Okay, they're both positively charged. What in their nuclei is making them positive? They're protons. Their nuclei are getting too close together. What else, and this graph doesn't tell us this, but what else would repel each other if they're getting too close together? The electrons, yeah. Okay, so this would be them too close together. This would be them not close enough. This would be that perfect, happy medium. And ladies and gentlemen, this is a beautiful illustration of a good life lesson, okay? This is a perfect illustration of being in a romantic relationship with someone, okay? Here's you. Here's the love of your life. Here's your romantic sidekick right here, okay? Do you want to be close to them? Absolutely, okay? So you want to spend time with them. You spend a lot of time with them. You spend a lot of time with them. Oh, now you're spending way too much time together. Way too much. Okay? Ladies and gentlemen, it is not healthy to spend 24 hours a day, 7 days a week, 365 days with a person. You will start having forces of repulsion. Good life lesson. Okay? There's a happy medium in every relationship. The fun is finding where that happy medium is. Okay. Moving on. Okay? All right. There's two types of bonds in this world, ladies and gentlemen. Ionic, what's the other type? Covalent. Okay. We're going to talk about both types in these chapters. Okay, but let's just refresh our memories. Okay, an ionic compound involves a metal and a non-metal. There is a full transfer of electrons when you have an ionic bond. All right, one element loses electrons, the other will gain those electrons. But guys, the point is, no matter which type, ionic or covalent, doesn't matter, things bond for the same reason, whether it's ionic or covalent. They are all trying to achieve what's called the NGEC, a noble gas electron configuration. Let's just review real quick. How many valence electrons does a noble gas have? 8. Okay. What's so special about noble gases? Why does everything want to have the same configuration as a noble gas? What makes them so special? Yeah, having 8 valence electrons is very energetically stable. Okay, so noble gases are kind of like the celebrities of the element world. When you're talking covalent, just to refresh your memory, we're talking about not a transfer of electrons, but the electrons are being shared between two nonmetals. Okay? And let's focus in on ionic for just a second, and we will get a chance to review for our test next week on this slide. Okay, ionic bonds, ladies and gentlemen, this is a term that's important for you to know. It sounds very complex. Electrostatic attraction, it's a very simple term. It means opposites attract. That's all that means. ionic bond is formed when oppositely charged ions attract to one another. And it's a very tightly, closely packed connection. And this is our good chance for review for our test next week. Okay. It says an ionic bond is formed when with an atom that easily loses electrons. Okay. An atom that easily loses electrons. Another way to say that, and here's where this review piece is going to come in, an atom that has a low ionization energy. Okay. So let's review, guys. Ionization energy, which you will be tested on next week, is the energy required to do what? Remove an electron. Very good. Can you tell me on our periodic table, left side or right side, which side has the lower ionization energies? Left side, okay. What kind of elements are on the left side? Metals, okay. And if something loses electrons, how do we name that ion? If it loses electrons, it's a cation, okay? So metallic cations react with something that easily gains electrons. And this was something that was at the very end of chapter 7. Electron affinity. Okay? What's a family of elements that would very much like, and don't use that word on the test because elements don't have feelings, but where is a group of elements that readily gains an electron? Your halogens. What kind of elements are halogens? They're not metals. They're nonmetals. Okay? And something that gains electrons, what kind of ion is that? An anion. Okay. All right. So these are some terms that we saw in chapter 7, and we will continue with more review in just a second. Okay? And in an ionic bond, guys, electrons are fully transferred. There's no sharing of electrons. That's covalent. Okay? Don't write that equation down. It is not on your equation sheet. It will not be on your test. It is just some mathematical proof. Okay? This is something you might encounter in physics. I don't know. You may or may not. And I'm going to use as an example, we're still talking an ionic compound here. I'm just going to use this very simple ionic compound, sodium chloride. Okay. What's the charge of sodium when it's an ion within a compound? +1. Okay. How about chlorine? -1. Okay. This equation here, this is energy. Q1 and Q2, guys, these are the charges of your ions, and this is the distance between them. This is bond length. Don't worry about this number, just know that it is a positive number. Can you guys tell me, please, if I was looking at this particular ionic compound, plug in the charges of the ions, forget about what the number would be here. If you plug into your calculator 2.31 times 10 to the -19th times 1 times -1 divided by some kind of positive number, what result are you going to get? You're going to get a negative answer. What's a negative energy mean to you? It's exothermic. Now see if you remember this from thermochemistry. Our exothermic reactions Are they typically favored or not? Yes, they are. They are typically favored. Guys, all I have done here is given you mathematical proof of why opposites attract. They attract because it is exothermic. It is likely to be a favorable process. That's all that is. I'm not going to ask you to do any calculations with that. Okay. All right. So we're just going to wrap this introductory portion up, and this is where we're really going to get into some good review for next week's test. Okay? This says, if we are talking about the trend on the periodic table, not for atomic radius, but for ionic radius, it says ionic size increases as you move down a group. Well, guys, that's the same trend that we saw for atomic radius. Now let's see if you were paying attention. Okay. On next week's test, you will have questions where you have to explain why that trend is true. Okay? And you can't say because of the snowman. All right? Why is it that as you move down a group, move down the periodic table, why does atomic or ionic, it doesn't matter, radius increase? What's the AP Chem lingo way to say that? The reason why.
Energy level.
You got it. Increasing number of energy levels. Okay? Very good. Here's something else to think about. Let's compare these two particles. A sodium atom versus a sodium ion. Let's say you had a question where you have to tell me which one has the smaller radius. Well, first of all, what happened to get us from here to there? What happened? We lost an electron. You just used the word lost. Very good. Guys, if you lose weight, don't you get smaller? Yeah. This guy is smaller in size. Now, could you say that on a test? No, you can't. Well, if you lose weight, no, you can't say that. Here's how you would explain it. And this is good review for our test next week. Look on your periodic table. Can you tell me, please, and listen carefully to the words I use, how many occupied, not full, how many occupied energy levels does a sodium atom contain? How many? Look at where it is. 3. Okay? This has 3 occupied energy levels. How about this guy? 2. This has the same number of electrons as what element? Neon. 3 energy levels, 2 energy levels. Yeah, you bet this guy should be smaller. Guys, when you change even by 1 energy level, that is a big difference in size.
You also use the reason, like if you lose an electron, then the effective nuclear charge is larger because you have more.
Yes, you could. So that's definitely at play here. What she said was, could you use the argument that when you take an electron away, the effective nuclear charge is stronger? And that's absolutely true. That is happening. However, the fact that this has 3 energy levels versus 2, that's an even bigger deal. Okay? What if I asked you to compare these two particles? let's think about it. What happened to get us from here to there? What happened? We gained an electron. Okay, so let's go with your gut instinct. If you gain weight, you get bigger, right? And that's absolutely true. This is a larger sized particle than this guy. But how would you explain that? Well, look at your periodic table. How many occupied energy levels does fluorine have? 2. How about this guy? 2. Okay, so we can't use that as an argument. They have the same number of occupied energy levels. Do they have a different number of protons, maybe? No. The issue at play here, guys, is something called electron-electron repulsion. Okay? We have added an extra electron. Think about it as like, if you have 7 people standing around in a circle and they're holding hands, and an 8th person wants to come in and join the circle, you have to back up a little bit to let them in, don't you? Okay? Well, from an electron perspective, this extra electron that's coming in, it's a like charge. Like charges repel. And when things repel, they tend to back away from each other a bit. So, technically, that is why this is a little bit larger than this one. Okay, now, let me bring up a picture of something here. Do I have it on here? Yes, I do. Okay, good. We talked about ionic radius up and down. Let's talk about it left to right. Okay. Now, guys, let's review. Before we even talk about ionic radius, let's see what you remember from last class, hopefully. Atomic radius. Left to right. Do atoms get bigger or smaller? Smaller, okay? Tell me, not ionic, we're talking atomic radius. Left to right, what do all of those elements have in common? They're all on the same energy level, but every time I move a little bit further to the right, what's happening? I'm gaining one more proton, which makes what stronger? Effective nuclear charge. You got it. Okay, good. Well, let's look at what's happening here. This is row number 2 on the periodic table. And this looks kind of weird. I want you to focus in on 1, 2, 3, 4. Just these first 4. Okay? Can you guys tell me, please, this ion right here has the same number of electrons as what element? Helium. How about this one? Helium. This one. Helium. Helium. All 4 of these particles, ladies and gentlemen, have only 2 total electrons. All 4 of these particles only have 1 occupied energy level. Why are they getting smaller? They all have the same number of energy levels. How come they're getting smaller? Okay, it's for the same reason we just said. Increasing number of protons and thus what? Thank you. You can either say a greater effective nuclear charge or stronger. That would work. All right, let's look at these 3. This has the same number of electrons as what element? Which one? Neon. This one? Neon. This one? You got it. These 3, you guys tell me, these 3 have how many occupied energy levels? 2. And why are they getting smaller? Yeah, for the same reason we just said. Increasing number of protons, we're getting a stronger and stronger effective nuclear charge. Now, These elements are all in the same row. Why is there this huge jump in size? And this is not to scale, ladies and gentlemen. This difference should be much, much bigger. But why is there this such huge difference? Yeah. Yep. These first 4 cations, remember what we said, these guys only have 1 occupied energy level. These have 2. That's a big difference. It may not seem like a big difference to you, but it is. Okay? So we see an energy level change from here to here when we go from cation to anion. Okay, there's a vocabulary word I want you to know. Isoelectronic. Does anybody know what the prefix iso means? It's a word that starts with an S. Same. Okay, like an isosceles triangle means a triangle with 2 of the same sides. Okay, isoelectronic, same electrons. Okay, ions containing the same number of electrons. That's what isoelectronic means. Okay. Here's an example of a list where all of these particles all have the same number of electrons. All of them have 10 total. All of them have the same electron configuration. Do you think, you go with your gut instinct, people, do you think they are the same size? They are not. They look like that. Why? Let's use some of that AP Chem lingo that you're going to use on the test next week. Why is the aluminum ion the smallest? I mean, they all have the same electron configuration. Yeah, why? It has the greatest number of protons. It has the strongest effective nuclear charge. All right, this is your last task for the day. I want you to put these particles in order of decreasing size. That means you put the largest one first and the smallest one last. Try it. Are these particles isoelectronic? Yes, they are. Very good. Okay, what do you think? Which one is the largest in size? What do you think?
Phosphorus.
You got it. What's next? Yep. Then argon. Then what? Okay. And calcium is last. Let me ask this a little backwards in the way that I have been asking it. What does isoelectronic mean again? They all have the same number of electrons. Why is phosphorus the largest? That's a little backwards than I have been asking. It has the fewest number of protons and thus has the weakest effective nuclear charge. You got it. I'm going to stop there.